Welcome back to Within Tolerance, a podcast for machinists by a machinist. I'm your host, Dylan Jackson of Protean Machining, and this week I'm very happy to welcome back Jonathan Hornell-Kennedy. Welcome,
Thanks
Jonathan.
for having me.
Yeah. So it was funny. I posted your framework stuff for questions. Had a few people reach out and they're like, I don't know who this guy is, but yeah, it looks good, interesting. And I was like, no, I think you probably do know who this guy is. You just don't know his other company. So let us know who you are, what you do, and yeah, give us all the info.
Well, yeah, last time I was on the podcast, how long ago was that? Like 4 or 5 years?
It was a while ago, yeah.
Yeah, like pre the world blowing up with the pandemic and everything.
Yeah.
So, yeah, that was as Core Print Patterns, which still exists. I'm just not posting all that much on that account since all the interesting stuff I'm doing definitely feels like it's with the bikes. So that's the framework account. So yeah, what do you want to do? Just like fill in the timeline since last we talked?
I don't know how these points connect. You know, you got molding and you were doing robotics and injection molding and you know, all kinds of crazy stuff last time we talked. And then like, I didn't even realize that the framework stuff was you. And then I think I was talking to Easton and he was like, man, have you seen all the cool stuff Jonathan's been doing? And I'm like, I don't think Core Print Patterns is posted in a really long time. What are you talking about? He's like, no, the framework stuff. And I was like, oh.
Yeah, I tried to put up like a hard post with like, check out this other account. I feel like Instagram has changed so many times in the last couple of years of like how they promote stuff to people. So it can like fly under the radar. So yeah, last time we talked, I was like, we're just trying to get our aerospace stuff set up. And was definitely like heavy in production machining and foundry tooling. I don't think we had started any of the injection molding stuff at that point because that was like COVID response type thing. So
the last time you were on, I just found it was January 2021. So yeah. How do you get from there to here?
Yeah. So I think when we were talking last, we were just in like the final kind of steps of getting our AS 9100 accreditation. And it was kind of like, yeah, let's talk in a few years and let you know if that was a worthwhile pursuit or not. So for us, I would say it wasn't. We've like just last July, it was like, okay, do you want to renew it? Here's your $15,000 invoice. And it hadn't really given us any, new business opportunities that was worth the cost. And honestly, Elise was the one doing all the paperwork. So like the burden didn't really fall on me for any of the headache. But yeah, so just to, if anyone was waiting, for that answer from how many years ago. So yeah, we were just kind of doing our thing, trying to add machines, do that's, the kind of like growth thing, try to get more business, more capability. And then what happened? I started actually doing my PhD in mechanical engineering at a local university.
Oh, wow.
Yeah. I kind of talked about it a little bit, but not a whole lot. I kind of kept it under the radar for the first year or so. And so I was researching with, like my supervisor there runs a facility called the Manufacturing Research Institute. And it's a big machine shop. They do a lot of process stuff with like big companies like tier one automotive OEMs. Things where can we optimize, like you're literally making millions of one part a year. Sort of the opposite end of the spectrum from what like most of the people listening to the show probably do. But yeah, so was there in school. Things were going well, trying to run the company at the same time. It was a bit of a stretch. And then the pandemic happened and it was like, okay, so one of the main reasons I wanted to go do that was like my work is somewhat isolating. Like people don't really know what I do for a living, friends and family. And then, I work alone like 60 hours a week, right? So I was like, oh, there's this group of people who have similar interests and are like aligned with that type of stuff. Cool. Might be able to make some interesting connections and, whatever. So as part of wanting to have a different type of fulfillment, I would say. And then the pandemic happened and it's like, okay, you're not coming to campus anyways. And the world's kind of ending. So business was not ideal during that time, I would say, the beginning of the pandemic. There was a lot of like A lot of the work we do in terms of the tool and die stuff is, one-off work, and it's people are only investing in that stuff when they're kind of feeling optimistic about the future, right? You're not getting a new mold built, you're not designing new parts, whatever it might be. So that kind of all slowed down a bit. We're still doing some machining work. But because my supervisor was running this big kind of manufacturing, like the general public doesn't know what they do in there, right? It's a machine shop. So everyone's coming to them with like, hey, can you make this ventilator part? Can you make these face masks? Can you make X, Y, and Z, whatever, right? So there's this constant stream of people coming up with things that needed to be, that the world felt was very important to have at that time. So I kind of said, hey, you know what? Like, I've got some experience designing molds. Let us know if we can help with anything. And kind of left it at that. And then like a pretty legitimate researcher from like the medical side of the university was big into running like the virology labs and was very familiar with like all the PCR testing stuff. Like we're public healthcare up here, right? So it's run by the province and they kind of have their labs all over the province and they couldn't buy stuff for them, right? So this virology researcher came to my supervisor and was like, hey, here's this list of parts that we need made. Do you think you could help make them? And they were all to do with like nucleic acid extraction and kind of like labware. And so that's how the whole injection molding thing started. I was like, I'll help you design the molds. And then we were trying to have the parts actually injection molded at like automotive places around here. And auto places, and the requirements for medical are not
yeah.
You walk into some of these places and they have like 50-gallon drums on the floor to catch the leaks out of the roofs or whatever, right? Like they're not, they don't, it's, injection molding is a tough business to run, I feel like more so than CNC job shopping. So anyways, then it was like, okay, so we're having trouble having people take this seriously. And should we just get an injection molding machine and try to figure it out ourselves, whether that's at the university or the hospital or here? So we volunteered, and then, we applied for a grant from the provincial government to make, they're called like deep well plates. I've actually have each year. I've got one that I use for like holding end mills. So it's, I don't know, 2 inches by 3.5 by 5 inches long. And there's like 3/8 inch-ish holes that go, it's like 98 different test tubes or 96.
Right. I think most people will remember you posting so much about that because didn't Danny make the pins for it as well? And
Danny made the core pins, and then Adam the machinist, helped make some mold inserts for some of the earlier parts and blanking out, like doing some grinding before we hard milled some of the components. So it was like a little bit of a team effort there.
It was really cool seeing everybody collaborate, Dan, Adam, you all trying to make this work.
Yeah. And for like, this was over, I don't know, probably 1.5 years, 2 years that we're working on. So the original family of parts was like a dedicated set of consumables for a particular machine. So think of it like having to buy your replacement ink cartridges from Epson or whoever you buy your printer from, right? So it was this like turnkey piece of equipment that I guess the OEM hadn't taken out any patents in Canada because they just felt like it's too small of a marketplace. So the powers that be felt like, okay, we can actually take a shot at just trying to like make our own parts because we're not really open to any liability. So that's where it started. And it was like a really interesting problem. But like the whole time you're up against like, we need these things because we got to save lives or, like we really felt like we were doing something important and meaningful at that time. So it's disheartening that like it was just filled with like setback after setback after setback from us and from other people in the team. Like it was about making the reagents, so the actual chemicals that go in there. We were on top of like making the plastic parts, and then there was a third party making these nanoparticles that go in the solution. The way this particular system extracts the DNA from the sample is like there's tiny little nanoparticles that are half silicon and half iron. And they can chemically make the DNA bind to the silicon side of it. And then they use a magnet to pull the iron side out of the solution. Yeah. So it's like very cool.
That's crazy.
But we could, if we substituted any one of our parts with the 2 other OEM components, we could get it to work. But like when we used all 3 of ours on our own, just couldn't make it happen. The stuff wouldn't break the fluid film, like whatever surface tension was on there. So yeah, then it's like, well, throughout this struggle, we're kind of going, well, does the province, like how many machines does the province have that actually use these parts? And aren't there more like the generic robots that are used in labs look kind of like a really high-end FDM printer. They're like a gantry machine, and they have a crazy head with the pipette tips that can come down. And then the work surface is like, they literally use software that looks like Excel. And you kind of say what reagents are in what cell, and it'll go, it can titrate, it can move stuff, it can throw the plates out, grab new ones, whatever. So it's just like a Cartesian automation system. So if you're a researcher, you could do whatever you want with it, but you have to be able to buy like the plates like this, right? And then there's like, the reason there's gaps in between them is the magnets can go up in between there. You can have heater plates that can move it all around. So those machines are everywhere. So we said, hey, what are we doing making this like one proprietary thing? Let's just make those parts that are used kind of universally throughout the country. So that's when we applied for the grant to get the molding machines that we have in the facility now in the clean room set up. And that was predicated on like our Ministry of Health giving us a purchase order to buy, 100,000 of those plates or whatever, right? So that was the mold that like really kicked my ass. Like that part I didn't realize because I went into it not, knowing a ton about injection molding, but like I showed that part to people after the fact and they just like laughed. There's no way you could make that. Like it's just such a challenging component because the two sides of it intermesh like, 2.5 inches deep, and you've got core pins that are basically floating out unsupported, right? So when you've got 10,000 PSI of pressure in there, you deflect one of those pins and you go to open the mold. Like I have a mold up front that Elise is still like too emotionally attached to. That's just destroyed. We went to go to eject the part and put 50 tons of like force on the ejector plate, and the mold just like blew apart. Because I can pull out one of these core pins, so maybe I can. So yeah, there's like 96 of these in one side of the mold. And then there's a plate with holes for these with, I think there's 2/10 radial clearance. And that's what ejects the part. Because otherwise you couldn't use ejector pins to get like that much surface area. So like what happened was if you inject the plastic and it bends that over and it sets, and then you go to strip it out, you're cooked. So we had to add vacuum assist to the mold, and I had to gate it so the liquid plastic flows into that part 96 times at the tip of every one of these. I don't know if I've got a runner bar on my desk anymore, but yeah, so you have to have the plastic flow from the injection molding nozzle and branch out 96 times to the top of each one of these, and that path distance between them all has to be the exact same.
Holy crap.
Yeah. And that all happens in like that amount of space, right? So yeah, I had no idea. So, and ended up making our 100,000 parts. But in that time, the government, like the world had kind of gone back to a bit more of a normal, our Ministry of Health had said, no more blanket testing for anyone, no matter what. It's like, you kind of have to have a doctor's note or whatever, legitimate reason. So they went from doing, I forget how many, 50 to 100,000 tests a day to like 2,000 or 3,000. So in the kind of, everyone lost their minds phase of it, the Ministry of Health put out purchase orders to whoever said they could help. So we got the grant and the purchase order, but then like, because we struggled a bit to get it going, they're like, okay, well, we don't really need these things anymore, but instead of just giving you like a buyout or whatever, we're just going to ignore you. So there was like, and we had to finance everything for the grant. The way those work is like they give you some money to get going, but you put up the balance. And then once the project is complete, you get your rest of your payout, which as a taxpayer, I'm happy about because you've got some skin in the game. But what it meant was that we had someone who didn't want to pay us for the parts and we were out of pocket. And throughout all of this, our business had sort of declined naturally, but we were also focusing on this because we thought it was like super important to do. So yeah, we were in a position where we were insolvent. I got kicked out of school because I couldn't pay tuition. And the government was basically like gaslighting us. So it ended up working out in the end. We shipped the parts, got paid, closed out the grant, had a business that was sort of on life support. Like everything is still here, but we were just kind of burned out at that point. And that's when the bike started. It's like, so for the first time in my life, I had a bit of money in my bank account. And it was summer, and I thought like, okay, go try to buy a bike in the middle of the pandemic. That was a whole crazy other thing, right? Like, I don't know, like not everyone listening to this is a cyclist. So the world was crazy in so many ways, but getting bikes was one of those. So I thought like, hey, how hard can it be to try to like make something? So I made a super basic 3D model and just bought some like carbon tubes from McMaster-Carr, had a bike together in a week, and then started riding it around. And people were like, hey, that's actually pretty cool. Have you seen all these other builders using like 3D printed components to do essentially the same thing? And so then I started looking into it more and what those bikes were selling for. And the whole thing has kind of snowballed from there. It's like a little bit of a, what would I call it? Like a midlife retirement. Having some fun and burning through some savings, trying to make this work. Yeah, so with regards to the bikes, I think I make a really good product and I've got something to offer the marketplace, but I don't know if I'm like the right branding guy for that, right? The marketplace for bicycles is different than what I'm used to in like job shopping, where like quality is measurable. You can, like, there's a lot of intangible value that comes from branding and what people think of your product in that kind of consumer space. So yeah, I'm still kind of getting stuff up and running in terms of wanting to have kind of interesting and scalable sort of human free way of making the bikes. Like a lot of the boutique manufacturing in that space is highly dependent on a skilled operator or skilled people doing a lot of manual work, right? Whether it's welding or some other form of metal to metal connection or tube to tube carbon work or just like carbon fiber layup and molds. Those are all like really, really manually intensive production methods that, you know, to get a good result, you need skilled people paying attention to what they're doing all the time. So my whole thing was like, hey, can I use my skill set that I have built up over 10 years of running a job shop to try and make a bike with the things I know how to do? So in the kind of boutique manufacturing space of bikes, you have like the ultimate kind of high mix, low volume in a way, right? Like I'm definitely making a more streamlined product than I'm used to with the molds. All the bikes kind of look the same to someone who doesn't know what they're looking at. But each bike is a one-off for that rider's geometry. So the way you normally do that is just you trade your hours for, you know, laying out the tubes, cutting them, whatever. But I wanted to do that all kind of automatically inside of SolidWorks. So that's kind of the chronological story of how I got from when we last spoke to where I am now.
Okay. So yeah, let's get into a little bit about your frames. I know Steven asked, you know, what software are you using? You mentioned SolidWorks, but this is all parametric and fairly easy to modify per rider, like you were saying. So how did that idea come to you and how do you accomplish that like you do?
The reason I'm using SolidWorks is we use HSM Works inside of it. So to do what I'm doing, you would not be able to use, or at least to my knowledge, like disjointed CAD/CAM packages. Like you would need everything I change in the 3D model drives what the programming does. So I'm like all my toolpaths live there and they don't update until I change the geometry and basically say hit recalculate and go from there. So the very first bike I did was just like hard modeled right for my size. And then it was like, okay, well, you look at the bike and I'm not coming to this with a great deal of experience. Like I've biked my entire life, but I've not ever built a bike before. And I've not been a guy who like knows about every single nut and bolt that goes on to bikes and like all the different standards and all that stuff. So I definitely had to learn a bunch of that. But yeah, the way the model works is I kind of looked at like what is a reasonable range of values that a rider will have for their, you know, body. How does that determine what the bike needs to do? And then what type of mechanical components also need to interface with it, that's like tires, group set, that kind of stuff. So building out the model actually didn't take me all that long. It was probably a couple days. It's really like a lot of it's just driven by underlying 2D sketches. So, you know, a diamond shape is what a lot of people refer to a bike as. So those are your front and rear triangle. defining all that based off of fairly standard measurements is easy. So it's just like I've got a variable set up for everything, basically, like where the handlebars are. Like I don't know how many people listening are actually bike people, so there's like all the proper language used, but yeah, it's like how far do I want to be up and forward for my handlebars? Where do I want my seat relative to where the pedals are? How long a wheelbase do I want? All those things, tire clearances. The tube diameters I can actually change as well. That has an important implication for like stiffness from the frame for different rider sizes and weights and power outputs. So yeah, I wanted to make the bike be hit as broad an audience as possible. Without needing to, like, a lot of builders would have like their dedicated road bike, their gravel bike, their mountain bike, whatever. But my model can kind of do all those things across the spectrum of like rigid bikes. Like I'm not doing any suspension yet. So yeah, it's the programming again, that's sort of always a work in progress, I would say. Like you don't know how something's going to work until you actually rubber meets the road and you test it out. So it might be like It works fine for 10 bikes, and then on the 11th there's some little tweak that I want to make, and then that just gets rolled into the revision. But the first bike probably took me like a week to machine, where you're like face pressed against the glass of the machine, and like my computer's right next to it. So yeah, I built a Lisa bike for the first one of like the real, like the parametric ones, and then yeah, I just started going from there. I think I made about 20 bikes last year.
Awesome.
Yeah.
So is this mostly done on the Matsura?
Yeah. All the components of the frame are done on the Matsura. It's a little bit of a part of the way I designed it was knowing that I was going to be milling them on a horizontal. So in the parametric modeling, I've got to maintain like orthogonality between certain features, so that like, if I can only rotate a B-axis or reposition a component certain ways, I need to make sure that my model doesn't do something that puts me into a situation where I can't machine it. So that's part of it. So the dream would be to have like, something like an MX330. That would be the ideal kind of machine to do the bike stuff. So yeah, like it's all those lugs are done on there. Make other components as well for the bike. Some of that's done on the Okuma. So that's the only new machine we got other than the injection molding machine since you and I last talked. I think you can.
Is that a 560V?
Yeah. Yeah.
Awesome.
Yeah, I can't say enough good things about it. We got that to do some of the mold work. The Mazak we have was definitely not up to snuff for the mold tolerances we were trying to do on the injection molding stuff. So we did a lot of it on the Matsura. But the issue you run into with like mold plates on a tombstone is that the top edge actually pushes back a bit. So when you're trying to hold a couple tenths flatness over like a 16-inch square, that you can see that right away. So we picked the Okuma because it's got the bridge kind of construction. And honestly, I it's probably my favorite machine to run. I can leave it for a month, come back, and it's like 1/10 away from where it was, like within measuring error.
That's
yeah,
killer.
the only weird thing about it is like it doesn't have auto greasing. So
that's very strange for something that expensive and that fancy. You would expect, a very basic option like that.
I know, but it's like it's their budget friendly line, which is like put that in air quotes because I don't like in Canada. As a Canadian, I can't speak to what any of these machines cost in the States because it's a bit of a distorted market up here for that. But yeah, like that machine, I think you would need to spend 2 or 3 times as much to get a machine that you could notice is better.
For sure.
It's like, to me, it's the best value in a 3-axis machine you can find anywhere. So I'll pay that small price of needing to go with a grease gun every month. But yeah, it is kind of funny. It's like I've never owned a machine that needs manual greasing before. But,
yeah, I think our early brother that we bought used needed manual greasing, but that's the only one I've ever owned that had that.
Yeah, so we make some of the bike components on there, like chain rings, certain little bits and actually, yeah, like these, I don't know, little headset topper things. A couple components I put in there, but again, it's like you're at the limits of what component on the bike actually wants to be a 3-axis component. So totally, most of the stuff I do on the Okuma is like one side, flip it, do the other side.
But imagine it doesn't make sense to add a fourth to that versus just, saving and adding a MX330 or something down the line.
I would, like, when we were actually speccing out this machine, we had people quote it with I don't know who makes maybe a Nikon 5-axis table or Pseudocoma. I don't know what they spec out on. And that's what we wanted this machine to do, like plate work on one side and mold inserts on the 5-axis indexer on the other side of the table. The issue was when they do that with the Okuma, they spec out a high bridge. So they put riser blocks under your gantry so that you've got dead space to the table, but you're not wasting it. So to put a rotary on that machine, I think the Z-axis becomes the issue. So when you have like some of the tools that I need to use on something like a head tube, like the front end of the bike, I've got like a 8-inch long tool that I'm using to go through from both sides of it, just so I don't hit stuff on the way in. So you can't do that on I think that if we had to put the 5-axis on that machine and had the taller bridge on it, I would have probably struggled through not having the pallet pool to do the bikes on here and just try to like sell the horizontal. It's a great machine, but it's like not the perfect thing for bike lugs. Like 5-axis is really what would make it a lot easier, but I'm not selling enough bikes yet to warrant trying to make that flip flop. And we still do some production machining on that, on the Metzer.
Gotcha. Yeah. Well, let's get into the other parts of the frame, because not only are you making all the metal parts, but now you're starting to make the carbon tubes as well. So Debris Brooms asked, what's your favorite custom piece of equipment you've designed and produced for framework? Carbon filament winder, molds, something new. Let's get into the other side of this, the composite side of your frames and all the learning and why you would even start winding your own carbon tubes in the first place, because it seems like so much work.
Yeah, I think I talked about this with Joe. Is like, if I knew how much work it was going into it, I never would have started. But like how like that's got to be universally true for how many people listening to this podcast, right? It's like you take it one day at a time,
probably.
As long as like 3 or 4 days out of your week are good days, then that's enough to keep you going. So yeah, the carbon tubes, like when I looked at like how our bike's made, what can I add? Like, I don't want to just be another guy making an expensive bike for the sake of having another expensive bike. There's a million of those out there. I kind of wanted to break the problem of making a bike down into like subsets and optimize each one of those areas. So I think that carbon fiber is a really remarkable product, and it's used heavily in bicycles, obviously, but where it isn't good is basically at each of the joints in the frame. So where I'm substituting metal in. The reason for that is getting carbon to kind of mold into complicated shapes is challenging, but then also ensuring that there's adequate strength around those sharp corners is hard. So like, I don't think any carbon bike maker would say that the tubes are what causes them headaches, right? The other thing about where I've chosen to put metal in the bikes is that's usually where there's also a mating component, whether it be, your fork, your crank axle, your wheels, whatever. So when you have an all carbon frame, carbon's just fancy plastic, right? It's pretty intolerant to abrasion resistance, and fine features don't hold well. So by using alloy for the lugs, I've got a material that behaves in a predictable manner. Like it's not dependent on how the fibers grow aligned inside of it. And it's also really good for like putting the bearings in, threading axles into. So when I started with the tubes, like, yeah, literally McMaster car, nominal inch tubing sizes. And then it's like someone from Rock West was somehow following us and was like, hey, we make this stuff for McMaster car. Can I send you some samples? I was like, hell yeah. That's awesome. Like, bikers are passionate, right? This dude's definitely like list himself. It's like, yep, sounds great. And start working with them. And so that's what the first couple bikes were made with their product. And then it's like, start to think about it some more. And I'm bringing them in from the States. So I'm paying US currency. I'm paying duties when it clears the border. and they're relatively expensive products to begin with for what they are. I thought, why don't I try? There's enough examples of guys filament winding tubes on like YouTube and other bike makers making like rep wrap based machines or modding 3D printers or whatever to make a filament winder. So for anyone who's not familiar, the way we make the tubes is the machine is kinematically similar to a lathe. We've got a spinning mandrel, and the carriage going back and forth has like a single strand of carbon fiber on it, and it's wrapping it like you would wrap hockey stick tape or, tennis racket grip or whatever. And so what we can do is by changing basically your thread pitch, you can lay the fiber down in different orientations to get different mechanical properties from the tubes. And that's all done automatically without a human needing to lay pre-preg sheets onto a mold or mandrel or whatever. So there's a lot of additional benefits to doing it that way over pre-preg. So it started with like, well, I can make one of those machines. It's literally a 2-axis lathe to start with, or 1-axis really, just carried back and forth on a spinning rod. So I spec'd out all the stuff from Masumi and ordered it. I actually had a bunch of servos kicking around from wanting to build like a large gantry for large format pattern making. And I didn't have the electrical skills to pull that off back when I got them. So they kind of sat on the shelf for 5 years. So had the motors already. And then I used an Acorn CNC to run the whole thing. And it just so happened that like the people I bought the servo motors from, DMM, they're based out of Vancouver, Canada. They have like a tutorial on their YouTube channel about like how to interface their motors with Acorn CNC, and they sell you the pre-made cables. And that was kind of like the barrier I couldn't get over. Like they're all like DIN 25 pin. I forget even what the standard is, where you got to wire up all your own cables. And that's where I kind of hit the wall originally. So getting those cables in, hooking it all up, getting it moving back and forth was one aspect of it. But then programming the machine to actually make the tubes you want is like a whole other challenge. Because you can buy software just like any CAM package. So there's tube winding softwares you can buy for, tens of thousands of dollars, and they'll make G code. It's all like inverse time kinematics for the interesting problem, because like your filament's coming off at an unknown speed based on the diameter of your surface footage basically. But as you go back and forth, you're also stripping fiber. So yeah, getting the machine up and going was like step one. And I had originally started with I'm going to use pre-preg tow, which is you're buying the tow, TOW tow is like what they call just the strands of fiber that isn't woven into cloth. And you can buy that with resin already mixed into it. The downside there is you've got to store it in a freezer, and then it has like pretty elevated temperature you need to cure it at, and it has a shelf life. And it's like all sorts of other issues that like really aren't taken into account that well in the bike industry, of like moisture ingress and humidity. You can't let it defrost too quickly, or you'll get condensation on it and ruin it, all that kind of stuff. So started with that, and it's really nice to wind because it's kind of tacky. But I was having a hell of a time getting the tubes coming out nicely, and that's when we started to like learn more about resin systems and how important that is to the overall carbon fiber product. Like the toughening agents you can put into resins that you're going to apply directly to the fiber. So then the other thing is the cost thing. Like the composites is a weird industry where it's really designed for huge consumers. Like you can't walk into a store and buy 10 feet of carbon fiber. Minimum order quantity is like $30,000 for some products. Jeez. Right? Yeah. And then that goes bad in a year. So you got to be sure you can make a lot of bikes. And this is like hundreds of pounds of carbon fiber, which translates to like a lot more than 100 bikes. Right. So yeah, then it's like, well, okay, if I buy raw fiber, that's the most cost effective way to buy the tow. And I can buy really, really high end tow because it's like, I'm not paying for someone else to pre-impregnate it with resin for me. And then I can pick and choose whatever resin I want based on, mechanical properties, how I want to process it. So yeah, learning about what type of an impact the resins can have on the strength, toughness, durability, fatigue life of carbon fiber composites is pretty interesting. And then trying to figure out a way to get that working in the system. So I basically made like a digital caulking gun to apply the resin. So I mix part A and B, I put it in a cartridge, and then I have like I think I ordered it off of Amazon, but you can buy those like little single axis stepper motors where there's like a extruded aluminum thing, bearing block, and then a ball screw. So that's what's driving the plunger on there. So I actually have it hooked up to the spindle speed output or the Acorn CNC. So I can dose
That's
like different amounts
crazy.
of resin. So yeah, like I might have the ability to put more resin on like different layers of the product as it's going down, because you'll have tension build up and it'll kind of squeeze down as you go. So yeah, the other thing that we do is like a lot of people, producers of filament wound products, they wind it on a mandrel that's like a very precise like chrome shaft thing, whatever. And then when they're done winding all the carbon onto it, they'll shrink tape it. So they'll go on with another head on the machine, or maybe do it manually where they're drawing tape on it. That's how they get their compaction. But that's only good for like, I don't know how many PSI, or some guys will vacuum bag it and you'll get whatever that is, 14 PSI of pressure. So what I actually do is I transfer it off the mandrel and then put it into a mold and put a silicone bladder inside of it, and then inflate that to like, depending on the diameter, we go from like 200 to 400 PSI on the bladder. And we also do that inside a vacuum chamber, because the way I assemble the bikes, the OD is what I care about more than the ID, the way our joint works. And it's also the show face of the carbon, right? Like people don't look at the inside of the bike really. So what you get with like shrink taping is less ideal composite, because whatever air got worked into your resin as you're winding, it's staying in there. You're just taping it down. You might like squeeze it a bit and get your fibers and everything nice, make your jam sandwich nice and compact, but you're not getting rid of that stuff. So by putting it in a vacuum chamber, I'll pull full vacuum on it, whatever. I think I'll go to like 29.5 inches of mercury. I'll let it sit for some amount of time before I pressurize the bladder. And so that gives us like a super consolidated composite with a really accurate outer diameter. So I don't need to sand off ridges from the tape and worry about filling pinholes and all that stuff. Like everything I'm trying to do is about streamlining the production so that human time is minimized, or at least it's isolated to things that don't take a particular amount of skill and paying attention type, tedious type tasks. Like talk about sanding and painting a carbon bike frame, like all carbon, like that's my idea of a nightmare. It's so easy to screw up, and it's like just you got to be be paying attention for like 8 hours or whatever it takes. So yeah,
right.
So the tube sort of at each step along the way, it was like, okay, I'm not quite getting the result I want. Let's introduce this next piece of the equation, where I tried to start it as simply as possible. It was just like winding right onto a silicone bladder and seeing if I could put the whole thing in a sandwich mold and blow it up. And so it was like, I've got shelves and shelves of test tubes that I've made that are, not quite there. So I've just now, I think within the last 2 or 3 months, really cracked the code on getting repeatable processes and starting to play with like really manipulating fiber angles and how many passes I do and where I put fiber down in the tube. Like I can change all of that stuff to get 2 tubes that look the same from the outside but have totally different mechanical properties, like super flexible, super rigid, very torsionally stiff or not. And those are all things that contribute to how the bike performs and handles. Yeah. The other thing is like they're super tough, like resilient to impact. Like a lot of carbon fiber bikes in the lightweight end of the spectrum, like if you knock them over by accident, you should probably have them like ultrasound tested for cracks, because under the paint something might start to go, because they're like so optimized that they just aren't built for, whacking it with your Allen key while you're working on the bike could be a problem for some bikes, right? So my tubes are definitely not like that.
That's so cool. So you kind of glossed over 2 things that I want to touch on. Building this machine, NTL Steven also asked, what kind of educational resources do you use to branch out into these new industries? You just watched YouTube videos and like read some articles and were like, yeah, I can make that machine. It's like it's a 2-axis lathe, sure, but there's, I feel like the handling of the fiber and having, that bearing system so that you can have that tilt as you're wrapping and all of that. Like this is not easy stuff to get right. So where did you,
Thank you.
how do you
YouTube,
approach something
you're
like
right.
that?
A lot of watching YouTube, just seeing how other machines work. And yeah, like adding so that the delivery head is what is like often be rotational axis on, I think, in the nomenclature that they use. That was like a later addition. For what I was trying to do was just have the fiber come, the sled just went back and forth, and then the fiber would kind of do whatever it wants to. The issue you have there is like, depending on how extreme your winding angle is, it's like, picture wrapping, masking tape or whatever around a cardboard. Like, if you try to go at a very shallow angle, you kind of naturally know you need to start laying the tape down a different way, or else like one side's going to pull and the other side's going to buckle. So that's, it was kind of like, I'm going to put that off for as long as I can until I learned that you have to I should have just started with that. It was lazy of me to do it otherwise, because I was intimidated of both how to mechanically pull it off, but also how to program for that. Like, it's pretty, like, the way I program the machine is it doesn't think it's a rotary axis. It thinks it's XY. So my winding patterns look like a lie detector test or whatever, right? Like the G code is just a squiggling line back and forth in X and Y. So I just go off to Y in infinity, and that's just continuously rolling. So I do a mapping of like whatever the circumference is to a linear dimension. And then that gives me one rotation of the tube. And then it just goes from there. So I think I had a bit of a breakthrough when I realized for like interpolated movement, like a G02, G03, I could put a Z dimension in there at either end. And so my B axis is just a Z. So what it'll do is the way you calculate the angle is actually pretty easy. It's whatever your winding angle is your kind of like thread pitch in a sense. So you want the head to be rotated so that it's lining up with, if you laid out the tube flat, say I'm winding a 45-degree angle, I'm going at 45 degrees across that sheet of paper that's continuously unfurling. So my head has to be at 45 degrees. So there's actually no calculation involved. It's like if I'm winding a really shallow 5-degree angle, well, my head just has to be at 5 degrees. So what I do at either end is I'm using G91, so it's all just relative. So I know if I'm going to switch, I just have to go double the angle back. So I just manually add that into each one of my winding programs.
Okay. So are you hand coding 100% of this then?
No. So I've got a 2D sketch in SolidWorks that I'll enter all the parameters. So it's like fiber angle, diameter, length of the tube, how many passes, all that kind of stuff. And it'll make my squiggle line. And then I'm using 2D contour as like the G-code output for that. And then I've got to go manually add in my Z movements at either end. But yeah, it's like 4 lines of code, because then it's just a loop. So you need to know, it's kind of like, think of it like mowing the lawn, right? You got, if my fiber is X, like I don't know, it's about like 6 mil wide or whatever. And you think about your tube, depending on how you are, like if I went all the way down the tube fully axially, like 180 degrees, I just take my circumference divided by the width of the fiber, right? And that's how many passes I need to go around. As you start to skew the angle a bit, you just have to do like the trigonometry on what the one side of that triangle is. And that's how many passes, and you divide by that. So there are some like PDFs I found online from like universities for how to do those calculations. So a lot of it's pulled from that. It's like, I know people who don't like math, it doesn't sound basic, but it's like, it's just pretty rudimentary equations with a bit of trigonometry in there. And then once I had that breakthrough of like laying it out, like basically slicing down the middle of the tube and laying it out like a sheet of paper, like the tube is just a rectangle, right? Where one side of it is the circumference and the other is the length of the tube you want to make. And then you just have to fill in. And sort of like when you get to one side of the rectangle, you kind of instantaneously show up at the other side. But if you roll them around the tube, they meet. So yeah, right. That was like,
that makes sense.
A big breakthrough in terms of just being able to wind shallower angles and have the fiber go down really nicely. So the next thing that I'm working on is adding some sort of servo control to the actual tension on the fiber. Right now I have a passive system where like if I were to run the machine way faster in feed rate, I would probably have greater tension on the fiber just because it's like stripping off that. There's some friction throughout the system, right? And the faster you want it to go, the more friction there is there. So yeah, that'll be like I'm hoping the final thing that really like makes it super easy. Like right now, all the results I'm getting are great. The main thing with the fiber tension is that it'll allow me to like have more confidence when I want to make little tweaks of the program that's just going to go down nicely. So, and again, a lot of this doesn't matter nearly as much for us as traditional filament winding because I'm putting it in a mold after. So a lot of the consolidation that you get in filament winding is from ensuring that you have constant tension of a known amount as you're rolling it on the tube, because it's kind of like each subsequent layer squeezes down on the one below it. The other thing that's really important about the tension is the fiber impregnation of like how the resin gets in there. Think of like having a kitchen cloth or something and pulling it really tight, like your water's going to come out of it, right? And if it's really slack. So being able to control that accurately is a really important part of ensuring you have resin actually infused into the middle of your fiber bundle. Because there's in that tiny little 6 millimeter piece, there's like 12,000 individual fibers, right? So it's, yeah, like the fluid dynamics are not Newtonian to get the stuff in there. Weird things happen. And that's again why using toughened resins, a lot of the toughening agents in the resins are like tiny little nanoparticles. And you can't get them in something like resin transfer. Say I were to make my tubes of fiber dry, put them in the mold, and then you can pump resin in from one side to the other or from wherever. The fabric will actually filter out a lot of those toughening agents. It's like a super good filter. So
oh wow,
certain toughening agents won't work with certain manufacturing processes. So that's part of why like being able to add them like with such precision right at the right point. Other machines will do stuff where they'll like splay the fiber. So they'll have, it's kind of like an EDM machine in that you've got, you know, fiber moving, but needing to hold it taut enough. So some machines will actually have subsystems where they like bunch the fiber. So like if you took a rope and you push your two hands towards one another, it kind of splays out. So they'll do that on purpose to try and shoot the resin like right in there. Like they're called like toe spreaders. Yeah. So there's like, if you start to look on YouTube, there's so many videos of crazy machines being used. And it's not isolated to just carbon fiber. Like a lot of fiberglass structures are made that way. Like big, I don't know, water tanks or things like that. Big pipe sections for underground facilities or, you know, infrastructure. So there's enough kind of like, look, see what it looks like. How could I make that mechanically? So the delivery head, I just took like a McMaster-Carr pulley and bearing with the big enough ID and machined a step in the pulley so that it pushes into the bearing. So one half of the bearing is like fixed in the machine. The ID of the bearing has a pulley on it. And then my servo motor is just sitting off to the side and it just rotates with a belt, that pulley. And then it's just about configuring Acorn CNC to like, you know, have the right steps per whatever. And then,
right.
Yeah.
Let's talk a little bit about testing, because I know Valence Precision asked, you know, does this type of bike survive an overweight biker stress? And then NTL Steven also was asking about testing verification of the frame. So how do you go about testing these or you know, making sure that you feel comfortable selling these?
Yeah, we do fatigue testing to ISO standards. So there's like you know, you can buy a copy of the standards and they show you the testing procedure and an indication of what the machine needs to look like. Again, YouTube's filled with like video footage from these testing labs. So it's pretty straightforward. Like just have like an Arduino driving an air cylinder and then a couple load cells, you know, whatever mechanical, the test will cycle through different components of the frame itself. So one might be load is being applied to the front axle and you constrain the rear axle. And you've got to do that 100,000 times at, I forget what, like 500-600 newtons of force. Did the bike break or not? Okay. Next test. Pull down on the seat, you know, do like mimicking pedaling action. So that's like pulling down on both sides of the pedals and making sure that you have the kinematic loop to the rear wheel. So it's all about having like one part of the bike constrained, another free to float, and then the third is like where the force is applied. So yeah, we do ISO testing, and then again, the way we're making the tubes is a lot more robust than some other composite manufacturing methods. So there are different standards for road, city, mountain bike within the ISO. So the mountain bike stuff has higher loads basically applied. Usually it's the same amount of cycles, just higher loading. So those are all things we do. You know, I'll get questions from like young engineering students and stuff of like, how do you go about designing it, like knowing it's going to work? And it's like, it's kind of underwhelming in that it's like a guess and check kind of thing. Literally, like there'll be, especially when you get into all carbon frames and the failure mode is happening somewhere in the frame, they might just go, okay, go slap a bit more, another layer or two of 3K weave in there and hope that it doesn't, you know, it's like, it's not as deterministic as an engineering student might want you to believe. But I'm also not basing weight on my frames. Like you can get carbon frames that are very well made down into like the 600 gram range for a road bike. But my frames tend to be up in the, 1100 gram range. So almost double the weight. It's still very light, but like your safety factor is just like so much higher. And again, with the metal lugs, like a lot of the failures might happen in the joint areas, or typically the tubes in the front triangle break like a few inches back from the head tube. So just making sure that there's enough strength in all those areas. The other thing about ISO testing is like, a 100-pound rider who can't put out a lot of weight doesn't necessarily need to be on a frame that passes ISO testing. Like they're never going to fatigue it, right? So there's also like a whole bunch of other failure mechanisms. Like if you were to take a baseball bat to your down tube on your bike and whack it a couple of times and then go ride it, and that's very different than just 100,000 really nice push-pull kind of. So yeah, we do what we need to do for litigious reasons, proper testing and have the strain gauges like measure it all and record it. But really in a lot of ways, the bikes are somewhat overbuilt. So yeah.
Awesome.
I hope that answers the question.
I think so. Have you had when you were developing the bike, any spectacular failures testing out?
No, nothing really exciting. Like I made myself a bike with tubes that were, I can say now with confidence that they were too thin because I cracked the frame in half riding it. But it's like nothing I would do for a customer. I made, I tried to make the tubes. They were like, the wall thickness was like 30 or 40 thou.
Oh, geez.
Yeah, on a gravel bike, which is like maybe you get away with that on a road bike, but I was riding on like a mountain bike trail and went to go jump over a bunch of stumps and just hit my front tire and just heard this like popping noise. And I couldn't, like the fork looked fine. I couldn't figure out what was going on. And then on my ride home, I looked down and my top tube was just cracked. So I put the machine in the fatigue tester after that and saw how long it would take to break it apart, and it didn't take too long. But yeah, nothing too crazy. Like I said, a lot of the stuff is overbuilt. I think there are a bunch of builders using SLS prints instead of milling because, milling shapes like the lugs is actually pretty challenging, and printing doesn't pose the same kind of skill set, I would say. Like you don't need to, like, I know it's not a simple hit print, but it's not like programming the printer to mill it. So I think that what happen in situations like that is the average consumer and even some engineers might not be aware that like SLS prints can have the same ultimate tensile strength, but they don't necessarily have the same fatigue properties. They're more like aligned with a casting than they are with like a wrought or billet product. So if you were to say, I'm going to pick my lug wall thickness based on kind of industry standards for what an aluminum part should be, and you print it, you might end up with fatigue failures that are kind of don't make sense to you, but it's because the alloy itself isn't as pure in some senses, right? There's more microporosities, little like crack nucleation sites all throughout it. So I think that if we were using, like, part of the reason for using billet 7075 from like aerospace grade lab or mills is like, we know the material is going to behave predictably. So when I make slight tweaks to a rider's frame and the bottom bracket angle is whatever slightly different, I don't need to, test that because some layer line in the printer is now in a different spot and it could cause some unforeseeable failure mode. So yeah, totally. Like you kind of need to overbuild slightly with 3D prints. So I think like for anyone listening that does do that, I think some people have probably learned that lesson on their own. They've been doing it for longer than I have. But, adding a couple, like, half a mil to a mil on your wall thickness, it's probably a pretty safe bet. Yeah, there's some weight penalty, but again, that's why a lot of the parts have crazy infill in them compared to just being hollow. It just really helps. You couldn't 3D print a tube and have it come out nearly as strong as a piece of bicycle tubing. That's just not going to happen. So,
that makes total sense. Speaking of milling, Jeff Burke asked, good surfacing strategies for multiple cylinders coming together on a part. You've got a lot of those on your bike. All the parts look fantastic. So what's your go-to strategies, when you've got multiple cylinders meeting at a fillet?
Well, a lot of that is back to like mold making, right? So everything I made in the pattern making side of things had a draft angle on it. So 3D surfacing is just, in a way, second nature. It's a lot of like contour and scallop toolpaths, I would say, knowing how to constrain them so that they overlap and are always going to. Part of the issue with it is like the lugs change every single time. So you need to have a toolpath strategy that's going to accommodate for those changes within reason. So again, that's why I'm using like a integrated CAD CAM system, because I think you'd have no hope in hell of doing this like in whatever modeling and master cam or whatever, right? So yeah, the I wouldn't say a particular tool path is what's important, but the strategy I always take for sort of predictable outcomes is like rough, rest rough, finish machine, or like semi-finish finish. So the majority of the time that those parts, I think it's about 30 hours of machining for a bike frame, typically, between all 5 of the components that is comprised. So probably 70% of that is surfacing. So typically what I'll do is like, rough to whatever, pick a number, 20 thou, make sure that I'm in there with a tool that's the smallest feature size. And then it's ball milling everything. And typically I'll like rest rough to, I don't know, 4 or 5 thou everywhere, with maybe a slightly more coarse step over than I'd use for my finishing pass, and then finish at whatever you want to get the surface finish you need. Really, it's about giving that final tool consistent material everywhere. Because even with like, you'll get deflection as you're changing directions and loading the tool more. Like it's a 3D surface that's changing with that much topography without a 5-axis tool path where you're going to be able to like, lean everything over and have just a consistent amount of engagement absolutely everywhere. It's really important to make sure that on your finishing pass, you're not giving that tool more material than it wants to see in a corner or something, and it chirps and you're just like, your whole part is cooked at that point. So yeah, like a lot of times I'll rough with like relatively small tools that you look at it and go like, you could plow out way more material with a big tool. Part of it is like, there's not a lot, like these things are light when they're done, right? There's thin wall sections. So a lot of it is about order of operations. So you don't have this cantilever workpiece holding on by a couple tabs that's just vibrating like crazy up top. So you either have to like work towards your fixturing or, a lot of times what I'll do is I'll actually finish the whole exterior surface before I take any material out of the inside. Just so that I can, like, the outside accuracy wise doesn't need to be very high, a couple thou here and there is fine. Like if you saw what most people are doing with their 3D prints, like bench grinding them just to make them look half decent. It's like, it's a bike at the end of the day, right? I'm chasing tolerances that sort of don't exist in the industry. So as long as the outside looks good, then you can go after taking the material out of the inside, which is where your accuracy matters. But then again, as you get down to the bottom of that, you've got like the thing's a shell of material at that point, right? So yeah, part of it is like going back to how we do the parametric modeling and making sure it all kind of works out. And the design of the bike, it's also designing the fixturing into the component itself. Like a lot of I'll get guys telling me like, you're lying. There's no way you did that in a single work holding setup. Like, and there's some stuff I'm not showing on Instagram, right? Partially because it's like the bike audience doesn't care or it's not impressive to them. So like, I'm always happy to talk to most machinists when they're like, hey, what the hell's going on with that? Like, so we'll do stuff where like, you got to go in and bore a hole through the bottom of the work holding, like in between the vice jaws after the fact. and then tab it off, things like that, where it's like you got to be predicting the downstream steps in your design so that you don't back yourself into a corner. Or like if I do need to do any secondary operations on the parts, it's always off of a component or a feature that doesn't change bike to bike. So things like where the axle goes through, or those things, like the whole part might change around it, but you've got some known datum that's going to be predictable no matter what the bike looks like. So and then probing, I use probing a lot to like find features, reorient, do some QC, like in-process QC, especially where we're putting the bearings into the frame. Like that's a whole contentious part of the bike design. But yeah, that's not a debate for this podcast.
I wouldn't even know where to start. Last question. Thomas Likes Light asked, what lessons do bicycles have to teach folks in the mechanical trades broadly? It seems like many machinists, engineers, technicians have an appreciation or background in bikes, and that bikes embody many principles of simple, elegant mechanical systems.
I'm going to just pull up that. I have a copy of that question. It's a long one. Right. It's cool to talk to Joe about that, because that was kind of his, like, Cobra Frameworks. That was his in, like bikes, try making bikes. Then that was sort of his way in. I don't know. It's a tough question to ask, in that a lot of the mechanical design choices in a bike, I wouldn't say are inspiring. Their margins come into it a lot, right? So it's like, it's a consumer grade product that is made at a price point where, like, often there's more emphasis budgetarily put into paint than there is in actually making the bike. So that's kind of like the thing I'm trying to be the opposite of, like, not like we paint the bikes with a pretty impressive product, but it's like, that's not what it's about. So I think if you have something like, how many guys start like tinkering on their car and that leads into something, I think that if you need that kind of excuse to start exploring it, that bikes can be a great thing. Like a good buddy of mine that I've made through this bike project went to university for nothing to do with any mechanical stuff, started working in a bike shop on campus, and then like bikes is his thing, and worked for 10 years in the industry, and then ended up going back to school to become a fully ticketed millwright. So I think, bikes are getting expensive, but a really good thing to do if you're like wanting to tinker is like buy used stuff. There is a lot of good lessons to be learned in terms of like learning about standards. So whatever those might be in the field of interest you have, of like, if I source part A, B, and C, can they actually work together? And a lot of that information can be challenging to find. It's not like there's a universal library of documents that says, here's what this looks like. But yeah, just like pulling stuff apart, putting it back together, tinkering, puttering, playing with what features can I add. I think there's a lot there, but I wouldn't say that they're necessarily a source of like inspiring mechanical design necessarily. There's always some gimmick being released, and I'm sure I'm guilty of that, depending on who you're talking to. But they're rudimentary devices, right? Like they're like a rolling bearing housing.
Right.
Right. So it is like, and there's a lot of kind of I don't even know, mythology built up around how they feel based on what materials used and opinions. So there's almost like religious camps within the bike world.
Well, that brings me on to shop news and new things. Anything else new or exciting in your world that's happening?
I mean, I'm pretty excited about all this stuff, so I appreciate being able to talk about it for a few hours, but we're just trying to develop more and more products to do with the bikes, and potentially whatever that might mean equipment wise. So again, this is more towards bike people, but like all the different components on the bike, trying to make as many of them as possible. Coming back to that kind of interfacing standards issue. And yeah, I think trying to grow that side of it. So if the bike stuff is of interest, I'd say stay tuned. Like I try to, well, I don't try. I post pretty much exclusively to Instagram stories, and it can be maybe repetitive, certain things, but it's trying to get through some problem solving and talking to Joe. Again, I think like YouTube content might be a good thing. So that is on my like to-do list, but definitely self-conscious. So putting myself out there.
Please do
format.
some YouTube content. I would love to see some videos.
Yeah, it's tough, right? It's like the type of stuff I would want to make, I don't know if it's perfect for the bike audience. So using it as a marketing tool for the bicycles could be hit or miss. But yeah, I think there's a right core followers that we have that like keep me going on that type of stuff. Like are engaging, interesting, have good feedback, all those type of things. So yeah, that's something that I'm slowly working up the courage towards, I would say. It's like, I thought I was going to like start the year off with a bang and, get a video or two out, but yeah. So I think that will come, just maybe might need to, take a bit of time to do it. Equipment wise, no purchases lined up. I think we are like, if I could somehow magically swap out the horizontal for a 5-axis, I'd do that. The injection molding machines, they haven't been turned on in like 18 months. So would sell those, would also love to come up with a product. Like injection molding workflow is so beautiful and it's running well. It's like the machine literally just prints money. It's definitely not that simple, but when it's going and you're not having to pick plastic out of molds or troubleshoot something, some friggin' hose bursts and leaks coolant everywhere. It can be nice. But again, like I'm looking at things through the lens of like biking right now, and a lot of products that would be made on an injection molding machine are tough to rationalize margins wise. But yeah, anything, someone's got some idea for a great product that they want to make, that would be cool. Be a fun video series of like making the injection mold, designing the part, commissioning it, get it working. But yeah,
that'd be killer. I don't think there's much out there in terms of end-to-end injection molding videos. Like it's especially on like large scale industrial machinery.
Yeah. There's a couple like John SQL or something like that, I think is the guy's YouTube channel. I can't really remember. He's got like some little hobby grade ones. He does a great job. But yeah, again, the components are like the really impressive components are the ones where the molds cost like millions of dollars. The stuff I saw like at the molding facilities we're at, like it just blows your mind that like something as simple as the lid on your ketchup bottle comes out of a mold that costs like $2.5 million. It's like filled with servos. And like, yeah, just really remarkable pieces of mechanical engineering. It was a bit eye-opening in that like you buy your CNC machine and it's worth whatever, and you put all your tool holders in it and everything. All your accessories are, pick some number, 25, 30% of the cost of the machine, where it's pretty common in injection molding for the mold to be worth like 2, 3, 4 times what the actual machine is running in is, right? So,
jeez.
Yeah.
That's nuts.
Well, they're big, they're expensive, they're accurate.
Yeah. That brings me to the last 2 questions I ask every guest every week. First up, what did you research this week? Doesn't have to be biking or machining related, just what's been popping up in your browser.
Well, fortunately it is. So then we're not going to get a change of topic here, but it's web tensioning stuff for the filament winder. So I've got servo. I can't tell if FedEx came in while we were talking. I've got a servo on the way. And yeah, what have we got? This linear potentiometer, and then a crazy air cylinder. So the idea with the active tensioning is that this is like, you've got constant air pressure in here and a pulley wheel. So your tension's going around it, and this maintains your web tension. And then the servo will be hooked up to the actual roll of fiber on the back of the machine, and it'll act like a clutch or a brake. So if the mandrel is like quickly accelerating and it's stripping more fiber, the brake on the thing will let off because this potentiometer is going to be pulled in a certain direction. So trying to get all that stuff implemented. Like this is an interesting cylinder that it's bore of its glass. Pistons are graphite. So that there's no
nothing magnetic?
No, not about magnet. It's about like no friction. because you
Oh,
want
okay.
that thing to, like, if you try to put like 5 psi into a tiny air cylinder like that, it just lurches around. The O-rings catch. So you're not going to get nice, even. The whole point of this part of the mechanism is to have a constant force on your tension. As long as the pulley wheel that's riding along this thing is anywhere within the stroke of this cylinder, your web tension will have whatever force this is pushing on it. So you then can control your tension with the PSI on the regulator that's attached to that.
Okay.
So
how does that, is that going to be relatively easy to integrate into the Acorn, or no idea yet?
It's on its own. It'll be like,
okay.
Yeah. So you set the tension just on it. Like there are advanced systems, like say you're in Creel, like your facility that deals with like film or paper, whatever. And you've got like one roll, your unwind and rewind rolls going on. There are a lot of instances where you would want to change the tension throughout. Like say I was winding really thick walled things. By the time you get to the outside, the tension is like massive. So you actually want to like change it throughout the process. I'm doing like at most 4 or 5 layers. So it's pretty linear across that. But yeah, like to have that all fully integrated with the CNC control would be pretty wild. But no, there's like, this will just be a standalone whatever. I think I might be able to do it with an Arduino if it's got enough sampling rate. But yeah, this will just be like flip a switch when you're ready to go. The tension's on and it just goes. The thing you got to watch out for is what happens to the servo motor if that web breaks. Like yeah. So
yeah, that could get sketchy, I guess.
yeah, they have like, I started trying to use like a bunch of the machines we've made have why am I blanking on the name? ClearPath servos, right? And you can run those in like torque mode, and then they have like in their configuration you can set a max RPM. So if it's trying to push in a certain direction and the web is broken, it won't go more. It'll fault out if it hits like 200 RPM. The issue with the ClearPath motors is they're like not that sensitive in a torque control mode, or at least the ones I have. It's like they're really like, I'm really at the low end of the torque that I need. And they were just, so I'm using the same motors that are exist on the machine already. So yeah, that's what I've been kind of trying to figure out.
Could you do something like a filament detection from a 3D printer, where just if it says, oh, there's nothing left, turn off this system?
Yeah, totally. You could have that just be like a kill switch in the whole thing. The web breaks, I'm screwed anyways on whatever tube I'm trying to make. I've yet to have that happen, right? It hasn't broken. I definitely very much like 3D printing. I don't start a set of tubes on like a very thin amount of filament at the back end. It's like, just there's so much work in getting the machine up and running at the beginning of the day. Like the last thing you would want when the resin's all mixed is to like run out of fiber halfway through a tube. There's no recovery for that, right? It's just in the garbage. So I'm trying to amass rolls of like tiny bit of fiber on them. So there's your product to come up with. What can I chop that stuff into and make?
Yeah.
Bottle openers or something.
The other question I ask every guest every week is, what are the things you're working on to be a better person, leader, employer, what have you? None of us are perfect. We're all working on stuff. What are you working on?
Oh man, I wish I could say I was noble enough to be focusing on that type of stuff all the time. Well, we don't have a big staff here, so maybe it's like my wife and I, right? So we had to put our dog down on Monday, and that was her dog for like 16 years now. So I would say just, hear that. Yeah, thanks. It's not a bid for sympathy. It's just like, I think trying to be very accommodating to her right now and supportive. Like I'm sad, but nowhere near as sad as she is. So, there's like always something going on for the person behind the account running it on social media, right? So I think interestingly, on the bike side of things, way more than on core print patterns, like the people who I interact with are definitely like a much higher frequency of bad apples out there, I'd say, of people who like want to tell you stuff or give you a hard time about something. I think bike people are very, very opinionated. It's not like the machining community, right? Where it's like, my experience with the machining community was very supportive. So yeah, like you're having a bad day and you're trying to put out something that you think are interesting and people just give you a hard time about it. It's like, that's tough. So trying to stay cool for those type of things, and yeah.
Okay.
So maybe that's not the answer you're looking for, but Yeah.
No. Those are exactly the kind of things that I like bringing up, because, like I said, none of us are perfect. I think it's important to recognize that, like you said, there are things going on in our lives besides the cool machining stuff that we're doing on Instagram. So I do very much appreciate that.
Yeah. And likewise for you, like the little conversation we had before we started about the growth in your business, right? That brings with it a level of stress. That is like, you're doing something excellent in this podcast, trying to make a community for people. But it's like, that's tough. It's got to be tough to do on top of all that other crap that piles on, right?
Yeah. It's a nice respite from all that stuff of talking to people like you and learning something and kind of getting away. I can check my phone. I'm in it. So I really love this kind of stuff. One more time before we close, let everybody know where they can find you online.
Yeah, so our website for the bike stuff needs a lot of work. It's not great, but it's frameworkbicycles.com. Social media account for that is Framework Bikes on Instagram. We're not on any other platforms right now. And then Corporate Patterns is the original machining one. But again, I'm not really posting much stuff there. We haven't had anything that I think is like interesting. All the stuff I'm working on is bike related. That is, I think, noteworthy. So going on that account. Yeah.
Awesome. Well, thank you so much for your time. Thank you to all the Patreon members that make the show possible and let me send people like Jonathan mics so you guys get good audio. You Patreon member Jeff, thanks for joining. Thank you all for listening, and I will be back next week.